In this video, we'll be analyzing a position time graph to figure out an object's velocity and acceleration. So note that position tells where an object is in space as a function of time. So we often think of this as horizontal motion. So x of t might be our position function. This tells us where an object is. Velocity is defined as the rate of change of position, so the position's derivative. And the rate of change is often interpreted as slope. So this will tell us the slope, or this can be interpreted as the slope of the position graph. Acceleration is the rate of change of velocity, so velocity's derivative, or in turn, the second derivative of position. And it's through this lens that we'll focus on this graph because we're going to be given a position function. So it's the second derivative of position, and recall that the second derivative describes whether a function is concave up or concave down. So the concavity of our original function, x, is going to be related to the acceleration value. So questions about acceleration deal with concavity of position. Questions about velocity deal with the slope of position. So our actual problem is this. I didn't fit it on here in the interest of space, but it gives us a position graph versus time. So where the object is at any time is going to be given by this graph. Now, going back a slide for a moment, notice what isn't being talked about here is the location of the object. Not really my concern. I want to know how quickly it's traveling and in what direction, but where it is, honestly, that's just reading a graph and not interpreting a graph a little more subtly as we're doing here in calculus. So we're looking for how quickly we're going through and in what direction we are going through certain locations. So directionality. Recall, the direction is determined by the sign of velocity. But velocity, in turn, is the rate of change of position, or the derivative of position. So really, through this line of reasoning, what we're thinking about here is the sign of the derivative, or the sign of the slope of the tangent line. That's what derivative means, slope of the tangent line, or just informally, slope. The sign of the slope at a given time, in this case, our time is at 11. So if I go to 11 on the graph, we have this dot. So the location of this dot is roughly, looks like -6-ish, but again, not my concern. I don't really care where this is. But what I do care about is, as we saw in this reasoning here, the sign of the velocity. So this is the position graph. The velocity is the rate of change going through that point. And you'll see here that this is a positive rate of change because this is an increasing function here. So I have a positive rate of change. My rate of change through 11, because of that uphillness, is a positive rate of change. So my sign of velocity here is going to be positive, and because I have a positive velocity sign, my object is moving to the right. Sometimes it might be moving up or forward. It depends on the context of the problem, but we're dealing with left-right motion here. It just doesn't say so on the screen. Now let's do a couple other examples while we have this graph. If I had asked, or if a question asked, well, what's happening at, let's say, at 6, right here? Well, I'm still in the negative region, you'll notice, but again, where I am, irrelevant. What matters here is the sign of the slope of the tangent line. That is a negative slope there, so in this region here at 6, or rather at that point 6, I am traveling to the left. And finally, one more example here. If the question had asked, what's happening or what direction are you traveling in at, let's say, 16? At 16, I'm in the positive half of the graph. Hooray, irrelevant. What matters is the negativity of the rate of change. So I'm moving to the left here. So this is leftward movement. This is also leftward movement. Oops. Anytime my graph has an uphill rate of change or slope, this would be a rightward movement. So slope, not value. Second question. What are the intervals over which the object is slowing down? So one thing to know going into this problem, just like how velocity was the sign of velocity was direction, in this problem you'll need to know going in that slowing down means this, that velocity and acceleration have different signs. So they conflict, either positive, negative, or negative, positive for V and A. So we need to find the velocity and the acceleration. And you'll notice in the previous problem, we sort of flirted with the idea of finding the sign of velocity. We had a positive velocity here, we had a negative velocity here, and so on. But in the interest of simplicity, I'm actually going to start with the concavity here first. So once again, I didn't fit this on the screen, just in the interest of my limited space here, but these little green dots are meant to signify inflection points. So this right away separates my graph into 3 distinct intervals. These are intervals of concavity defined or separated by my inflection points. So I have a certain kind of concavity from 0 to 8, I have a different kind of concavity from 8 to 12, and I have a different kind of concavity from 12 to 18. So this is nice because at a glance I can figure out what the concavity is. In that first region from 0 to 8, my concavity is concave down. You can tell this because the graph is frowning, so to speak. The rate of change is decreasing, to be more precise. In this next interval, my concavity is concave up. Comedy, and the next part we have tragedy, concave down again. Now this is sort of abstract in terms of functions. Our actual function deals here with motion, so when we're talking about the second derivative of position, which is what concavity is all about, as we saw here, the second derivative of position, working backwards here, I have now figured out the sign of my acceleration. Because of this concave downness, I know that in this region from 0 to 8, my acceleration is negative. And I know that in this next region from 8 to 12, my acceleration is positive because my function is concave up, so my second derivative is positive. And by similar reasoning, we have negativity here. So by just looking at the shape of the graph, we're able to figure out the sign of the second derivative, the sign of the acceleration. Since we need different signs for velocity in order to slow down, in order for them to conflict with each other, this tells me the kind of velocity I need. I need a different velocity sign in each location. So since I have a negative a already, I am looking for a positive v. Opposite here, and opposite here. So this is sort of backwards to part A. I'm looking for a positive velocity, whereas part A said, well, what is the sign at this number? Here I know what the sign I need is. So in this first interval from 0 to 8, so I'm only focused on this position, this part of the graph right now. In this part of the graph, I have a change in velocity at approximately 5. So prior to 5, I have a certain rate of change. After 5, I have a different rate of change. So before 5, I have a positive rate of change, which is exactly what I'm looking for. So from 0 to 5 is going to be part of our answer. From 5 to 7, again, within this interval, I have both a negative velocity and a negative acceleration. In this case, not what I want. My velocity here changes at 10. I'm looking for negative velocity because my concavity is upwards, so negative velocity would be moving downwards in this graph, decreasing. And finally, in the last section, I have concave, let me go ahead and mark this, sorry, so that's from 8 until 10. And finally, I have already established concave downness in this region from 12 to 18, so I would like a positive velocity, which means upward motion on the graph, or positive rate of change, or increasing, so that would be from here to here, or interval-wise from 12 until 15. So my final answer for this question would be from 0 until 5, in union with from 8 until 10, in union with 12 until 15. And that about wraps it up. Hope this helps.